So now that we know what the force is in a magnetic field, let's see the resulting motion from that. So reminder, we're only going to talk about moving individual charged particles. This isn't going to apply to currents really. So if I rewrite the equation, F equals QV cross B, or magnitude F equals QVB sine theta. Okay, so I have a particle moving to the right, positive particle, moving to the right in a magnetic field that points out of the page. So using my right hand rule, I can figure out the force. So turn my thumb so it points to the right. I need B to be away from the paper, so I rotate my hand so my fingers are pointing towards the ceiling. And I see my palm points towards the bottom of the paper. So the force here is to the bottom of the paper. Well, if something's moving to the right, but it experiences a force that way, it's going to turn. So a little while later, it's going this way. Well, now what's the force on it? Okay, so I need my thumb to point this way. I need my field to point out of the paper. And now my palm is pointing down and to the left. So my force is this way, which is going to make it turn some more. So now it's here, and it's going this way. And again, velocity towards the bottom of the paper, magnetic field out of the paper. Now the force is to the right. I hope you see a trend here. We're turning, and we would continue to turn. We have circular motion. The condition for circular motion is that the force points towards the center of the circle, and the center of the circle, that radial direction, is always perpendicular to the tangent, which is the velocity. So that this force produced is perpendicular to the initial velocity is what produces circular motion. So we can figure this out. Remember, for circular motion, centripetal acceleration, our basic equation, is v squared over r. So we can use Newton's second law. Make sure it's all on the screen. Net force equals mass times acceleration. Well, the only force on this moving charged particle is the magnetic force, QVB sine theta, equals the mass of the particle times its acceleration. Well, as we've just talked about, it's centripetal acceleration, so it's v squared over r. So here's the first thing that's interesting. One of the v's cancels out, but not both. I have set this up so that the velocity, because it's in the plane of this paper and b is out of the paper, no matter what direction the velocity is, it's always perpendicular. So this is 90. Sine of 90 is 1. So I don't have to calculate that. And then if I rearrange, I'm going to solve this for r. So r goes to the left. I'm left with mv on the right over here. And then I divide by qb. So I cross multiplied and then divided. And this is the radius of this circular motion. So if I could add that to the diagram. So if this is the center of the motion, this is the radius. And this is how you would calculate it. One of the things I want you to notice about this equation, the numerator is the momentum of the particle. Remember, P equals mv. So the bigger the momentum of the particle, the bigger the radius. And you can have more momentum either by a more massive particle or a faster particle. So if this particle had been moving faster at first, it would have made a bigger circle. If it had been more massive, it would have made a bigger circle. And then the denominator is Q and B. The stronger the charge, or the bigger the charge, the more it couples with the magnetic field, it said, the more force it feels. So the bigger this force, the faster it's going to change direction. So the bigger the charge, or the stronger the field making the force in the first place. So the charge and field together make the force. And so the bigger the force, the smaller, the bigger the charge or magnetic field, the smaller the circle. This has some really, really, really useful results. So we are going to go back to the same situation that we started with here. So this is B out, and positive Q moving to the right. And we know from our first setup, if it's moving to the right, magnetic force is down towards the bottom of the page. Now I'm going to put an M on there because I want to add something to this. We know the magnetic force from the right-hand rule, B is towards the bottom of the page. But I want to make this particle not turn. I want it to go straight through. But I want the magnetic fields to still be there. So the question is, what electric field would allow the particle to pass undeflected? I'm deliberately using this word. I could say allow the particle to pass straight through, but deflected or deflect is to move to the side, to change path. So undeflected, I want this to go straight through. I do not want it to curve down and to start to do circular motion. So I need to cancel out this magnetic force. That means I need an electric force, because I'm going to do it with an electric field, in the opposite direction. And I need it to be the same magnitude. So the thing I want you to remember about electric force is that it relates to electric field from the definition of the electric field. E equals F over Q naught. And we chose as physicists to define the direction of the electric field as the same as the direction of the force on a positive charged particle. So if it's a positive particle, the electric field and the electric force are in the same direction. So I need my electric field. Go away. I need my electric field to point in the same direction as my electric force. So that's the first half of this. I need crossed fields. I need a magnetic field to be in one direction, the electric field to be perpendicular to that. And notice also the velocity is in the third of the three directions. So I have an X, Y, and Z situation again. But you can figure out the direction of the electric field just like I did. Use your right-hand rule to figure out the magnetic force. Electric force has to be opposite that, and if it's a positive charge, electric force and field are in the same direction. Now let's talk magnitude. I need these forces to be equal. So I need Fm to be equal to Fe. Well, Fm is QVB sine theta. And Fe, if I rearrange this, is E times Q. I'm just going to write, because it's the same charge in both cases. So Q cancels, and this, again, the velocity is 90 degrees to the magnetic field, so this goes away. So I can solve this for V is equal to E over B. So physically, this is called a velocity selector. This particle will only go straight through if, one, the magnetic fields are oriented correctly, magnetic and electric fields are oriented correctly, and two, their strengths are related by this equation. So if it's moving too fast, it's not going to go straight through. If it's moving too slow, it's not going to go straight through. So we're going to put these two things together to make a very important device called a mass spectrometer. So mass, meter, we are going to measure mass, but we're not going to use it using a balance. Spectro comes from spectrum. So we are going to measure mass by spreading it out along a spectrum. And that sounds really interesting, but it's extremely useful. So we start by making a magnetic field. I'm going to use the same direction we've been doing. So, big magnetic field out of the page. But then we're going to break it into two regions. And we're going to put a little tiny gap here. So on this side, we're going to make an electric field pointing towards the top of the page. So this is the exact situation we were just talking about. If I have a positive particle here, and it meets the condition that its velocity is, wrong color ink, if its velocity is equal to E, the strength of the electric field divided by the strength of the magnetic field, this particle will go straight through. Now, if it doesn't meet this condition, it's going to deflect. If it's moving faster, it's going to have a stronger magnetic field, and so it's going to move towards the bottom of the page. And it's going to run into this wall. So this is if it's moving too fast. If it's moving too slow, it's not going to have enough magnetic force to cancel out the electric force. So it's going to go to the top of the page. And it's going to crash into the wall. So this side is our velocity selector. Only particles with this velocity get through this hole. Well then, when they reach here with this velocity, there's no more electric field, there's only magnetic field. So using our right-hand rule, we know there's a force towards the bottom of the page, just like there was here. This is the magnetic force. And so what we're going to see this particle do is curve in a circle, and it's going to crash into the wall. And we could calculate using R equals mv over qb. We know the velocity that it got through. We know the strength of the magnetic field. We're the ones who set it up. If we know the charge, we measure the radius, because this would be the diameter of the circle, so double the radius. So if we know where it hits, if we have a sensor right there, if it hits at this distance, we can figure out the mass of this particle. If a heavier particle with the same charge gets through this hole, it must have the same velocity. So a heavier particle is going to make a bigger circle. So it's got a bigger mass. So you're going to get a spread out of masses along this wall. The lightest masses will make the smallest circles, bigger masses and bigger masses and bigger masses. So we have measured mass by spreading it out along a spectrum, a mass spectrometer. And this is used all the time in atomic physics. You take a particle, you ionize it, usually singly, so it has a charge of equal to one missing electron, and you shoot it through here, and then you know what the species are. You can do this with molecules, you can do this with atoms. It's usually a low pressure gas that you do this to. And interestingly, it works for negative particles. Close the door. Yeah, close the door. Close the door. Don't come in. Don't come in. Close the door, please. If you have a negative particle, right-hand rule, velocity, magnetic field out of the page, we should get a force at the top, but electric force or magnetic force has to be the opposite because it's a negative particle, top of the page. But electric force for a negative particle is opposite the field. So again, as long as the velocity is correct, it's still going to get through. But when the negative particle gets here, it won't feel the magnetic force to the bottom. It's going to curve to the top. This doesn't usually happen, but if you did have both positive and negative in here, when they got here, the positive ones would go this way, and the negative ones would go this way. So again, it sorts out what the species are, and it sorts them by both mass and charge.